I think we're recording. Yep, we are. Okay. Now, yes, well, hopefully everyone who is not actually here, especially including those who are supposed to be here in Hattiesburg, um, are at least watching. Um, so everyone who has submitted homework 2, which was not everybody, still waiting on some of those, um, did all of us have been graded. Now the average was still quite high. Obviously not as high as the first one, where almost everybody got a perfect or near perfect score. But on this one, now the average was a 94. But I do have to say that in a number of cases, I was disappointed because there were a number of instances, especially really it was the coding problems, especially where it was just simply not following the directions. For example, mainly the last problem, so 3.2.20. So what I had in mind was to incrementally build on functions you'd written for previous problems, because you had a forward substitute function in your inventory. That was earlier in assignments. You had back sub. That was from homework 1. And then you had Gaussian elimination, which was first appeared in homework 1, was modified for homework 2 to store everything in a single matrix LU, which I might add for that problem, a number of people did not do. So all of these are meant to be used by SolveAXB. So SolveAXB would first call Gauss-Elim. Now this had to be modified for this last problem to do partial pivoting. So that was really the most significant part of a problem. And most people did that, so that was good. But once that was done, you still want to have what Gaussian-Elim was originally doing, returning everything in one matrix, U in the upper triangle, and then the multipliers in the lower triangle. And then SolveAXB would call that. So you'd call Gaussian-Elim, which would return outputs LU and P, an indication of how the rows were interchanged. I recommended in the hints, like a vector of indices. And once you had all that, then you could go ahead and call forward substitution. And then, so you'd have LU, but really you just use a lower triangle, and B, and also P, because the elements of P have to be rearranged, and forward sub produces a vector Y, and then that vector Y goes into back substitution. Producing the final solution, X. So SolveAXB could be done in literally 3 lines because it's delegating all the work to the other functions. But I saw a lot of people wrote everything within SolveAXB, didn't use what they had before. Some things I saw that were not Gaussian elimination as I presented it, like do a LU decomposition. It was doing something else, like reducing all the way to diagonal form. It made me wonder, like, was this code that was dug up somewhere, like looking online, which you really shouldn't do. Again, I did not investigate this, but I would be very unhappy if that's what was done. So this is the sort of thing that these problems are written the way they are for a reason, and I expect those to be followed. Points will be taken off. If I see this continue to happen, I'm not above simply giving a 0 for a problem. If I see flagrant disregard for directions that I put out there. If I say a function needs to be given a certain name, you give it that name. So just follow the directions. I can't believe I'm saying this in a upper advanced undergraduate graduate course. Follow the dang directions. Okay, so I'm serious about those. Another common thing was that I expected there to be difficulties with the first problem of proving that a product of matrices preserves triangularity, and also that the inverse of a triangular matrix is the same kind of triangularity. There were a number of instances where it basically amounted to assuming what you're trying to prove. When you look at the, for instance, for upper triangular, if U is your upper triangular matrix and X is your inverse, and you look at the product, which is supposed to be the ij entry of identity, and you want to show that X is upper triangular because U is assumed to be. So you at this point you don't know. So you could write this as a sum of like U, I, K, X, K, J, and what I saw was this broken down into three parts, like a part where like a subdiagonal part, a diagonal part, and a super diagonal above a diagonal part. And it is perfectly appropriate to assume that one of those sums will be 0 due to U being upper triangular. But then to say that the other, like the other sum, like the one above a diagonal, is also 0, you cannot do that because you don't know anything at first about the structure of X. Right? So it was a shortcut based on something you hadn't really established. So I could not give credit for that. There were different. Like I suggested one approach in the hints. Again, I put the hints out there for a reason. If you're just going to ignore them, then you're just making a problem harder for yourself. Now, I am open to other approaches, and like some people would go through this entry by entry and like show that there's a pattern that would like certain entries of X had to be 0, and you can show triangularity that way. That's perfectly good. So this is something I saw in a number of cases. That kind of proof doesn't fly. There's more to it than that. Now so the question was put to me. Now that you've gotten it graded, back graded, can you revise? So the answer I would give to that is that normally I would say from a time that I've set back a grade, but really starting from today because I'm making this announcement, that if you if you want to revise based on the feedback I gave you and turn it back in, I will let you do that for a time period of 1 week from when I send it back to you, or in this case, from 1 week from today. So you have that opportunity to fix this up. Now we're not in this case we're talking not many points on the line, but if you really want to do that, then go right ahead. And so that will apply in general with assignments for the remainder of the semester. So are there any questions about this assignment? If you're not sure what the hints are saying, or if you're not sure about the directions, that's when you ask me. I get so few questions. You guys are so quiet in class, and I don't get many questions out of class either. Maybe there should be more, because it's not like the assignments are going to get any easier. So please keep that in mind. I'm a resource too. Okay. So again, not a bad performance. Most people got, either an A or close to it, but things will get more challenging as we go deeper into material. Okay, so These are the sort of things I don't like to talk about. So don't put me in that position again. All right. Okay. So now, for the remainder of the time, continuing with iterative methods. Now, as a quick recap from where we were. So we're solving system AX equals B by an iteration that has this form, where instead of solving a system involving A, we're solving a system involving the matrix M, which would be preferably something that's diagonal or triangular, so the system is easy to solve. And we just keep carrying out this process to compute iterates x1, x2, x3, and so on, that hopefully will converge to the exact solution x, where x superscript 0 is some initial guess. And a little piece of terminology that I was unpleasantly surprised to discover I hadn't really made clear in the book, so I'll have to revise that. But so if a matrix called T equals defined to be M inverse N, that is the iteration matrix. That's an important term for describing stationary iterative methods, because it's the iteration matrix that the error gets multiplied by M inverse N as you go from iteration to iteration. So, and it's that error that you want to go to 0. Therefore, you have convergence if the norm or magnitude of T is less than 1 in some norm, like any of the matrix norms that we saw, like the infinity norm or Frobenius norm or whatever you want to use. Also, if and only if the spectral radius of T, in other words, the absolute value of all the eigenvalues, is less than 1. Which really is just absolute value of the largest eigenvalue. So as long as all the eigenvalues have magnitude less than 1, that is a necessary and sufficient condition for convergence. Okay. So that was a rundown on stationary iterative methods in general. And then there were 2 particular stationary iterative methods that were introduced. Oh, thank you. Oh.
Sorry.
Oh, dang.
I'm sorry.
It's the kind of day you've had, isn't it?
I'm sorry.
Yep. That's what modern tests do. That's what Dr. Cole should see this.
Well, at least it's not commutative algebra.
Okay. Okay.
Thank you for dumbing it down. Appreciate that.
He can't say nothing.
What?
I said until he takes modern algebra, he can't say nothing.
Okay.
Thank
Well,
you.
I mean, I have said this to him so many times. He gonna
Okay.
figure it out.
Thank you.
Okay. So first of these methods was a Jacobi method, where I won't write out the component-wise formulas again, but we just set m equal. So let A equal D plus L plus U, so the lower diagonal part, the lower triangular part, and the upper triangular part is in strictly lower and upper triangular. Then the matrix M is equal to D, and the matrix N is equal to minus L plus U. Keeping in mind that, actually, I'm going to fix this over here. A has to equal M minus N. That's the splitting. That I introduced that term last time. So M and N always have to satisfy that. So once you choose M, that determines N. Okay. So this is probably the simplest such method, but we saw that it was using out-of-date information. So we modified it to get Gauss-Seidel, where M is now equal to D plus L, so now contains more of A in it. But that's a lower triangular matrix, so it's still very easy to solve this system here. And then N is equal to minus U. So Gauss-Seidel tends to converge faster. It doesn't always, but it usually does. Faster than Jacobi, because it's using more up-to-date information about the solution. But so I'll indicate the advantage of each. That Gauss-Seidel uses the latest information about the solution, whereas Jacobi has the advantage that it is parallelizable. So it's precisely because it's insisting on using old information about X that you can compute each of the components of a new iterate independently of one another, therefore it could be done in parallel. Okay. So these are two methods that we're seeing, and so what I want to do today is introduce one more. So just as Gauss-Seidel is a modification of Jacobi, this third method is a modification of Gauss-Seidel. This is why I didn't bother rewriting the component-wise formulas for Jacobi or Gauss-Seidel, because I'm going to need to do it now. All right. So the third method, SOR, which stands for Successive Over-Relaxation. Now I see what people just call it SOR. Okay. So as a starting point to derive the method, look at the component-wise formula for Gauss-Seidel. So each component of a new iterate is equal to 1 over a diagonal entry of A times all this mess, Bi. Then we have a sum over entries of A times elements of the new iterate. Because we're computing component I, so components for J's component for J less than I is already available, so we could say xk plus 1. But then for J greater than I, similar sum, but we have to use elements of xk, because these components of xk plus 1 have not yet been computed. Okay, so that's just plain old Gauss-Seidel. But now I'm going to rewrite this as saying xk plus 1 is equal to xk plus something else. So I'll write xik here. So then I'm going to have the rest of this, but I need to compensate for including this. So I have, all right, so I have, oops, gotta watch my font size here. All right, so I have to fill in minus AII XIK, because here I have a 1 over AII out front, which cancels with this AII here. All right. What? Okay. Okay. Now, so you can think of this as this whole thing. So from this plus sign onward, you can think of all of that as the direction that we're taking to get from the old iterate to the new one. So the idea behind successive over-relaxation is, if this is the direction from where we are now towards the exact solution, if this is a good direction to take, maybe we should go further along this direction than just what we have right here. So in other words, we can multiply this by what's called a relaxation parameter. So what I'm going to do is I'm going to fill this in here. And I'm going to cross this out, because this is Gauss-Seidel. We're not dealing with this anymore. So SOR can be described as replacing this 1 here with a parameter omega. So that's an omega, not the letter W. Okay. These are my W's. These are curvy. Okay. All right. Now, so this is called the relaxation parameter. I'll talk more about how we choose that momentarily. But so now what I'm going to do is rearrange this. So this is how SOR can be written, but I want to write this in matrix vector form. So what I can do now is, if I write this as is in matrix vector form, I have xk plus 1 is equal to xk plus omega. Now, because I'm dividing by AII, that's the same as multiplying by D inverse. And now I have in here B minus, this is L xk plus 1. And then I have minus D xk minus U xk. Right. So here we have a matrix vector form of this method, but I want to get this a little closer to kind of form we saw for Jacobi and Gauss-Seidel. So I'm going to multiply both sides by D. So then I have, and the reason I'm doing that is to cancel with the D inverse here. So then I have omega B minus omega L xk plus 1 minus omega D xk minus omega U xk. Now I want to take all terms involving xk plus 1 and put them on the left side. Everything else stays on the right side. So that will give me d plus omega L xk plus 1 is equal to, and these terms involving d, I'll put them together. So I have 1 minus omega d minus omega u, all of that times xk plus omega b. So, so right here, and yeah, it would be nice to have a little room for this. Okay, but hey, it is the first thing I've boxed all day.
You haven't written much though. Got a long way to go.
Well, now it's a challenge.
Yeah, it is.
So this is a matrix vector form of SOR. So, so now we can use this to get the iteration matrix, the M inverse N. So now, actually, I haven't put up the iterations. I did last time, but not this time so far for Jacobi and Gauss-Seidel. So now we can look at all three side by side, or one on top of the other. Okay. All right, so iteration matrices. All right, so in general, when you have m xk plus 1 is equal to n xk plus b, then I can write this as just by multiplying both sides by m inverse. Okay. Now, so for a general stationary iterative method, M inverse N is whatever. So what you do is, if you write your method in such a way that xk plus 1 is isolated, and then M inverse N is whatever matrix is multiplying xk, that is your iteration matrix M inverse N. And then M inverse is whatever matrix that is multiplying B. So then you can invert that, take the inverse of that to get M. And once you have M, then N is just M minus A. So if you have a method where it's not really given to you what M and N are, if you write the method this way with xk plus 1 isolated, you can use these three tips to get M and N, and also M inverse N. I'm mentioning this because this is what one of the homework problems is about. It's a bit of a pain algebraically, but this is your roadmap. And I'll be writing up hints on this assignment, just haven't gotten around to that yet. Okay, so for Jacobi, we have so xk plus 1 is equal to d inverse and then minus L plus u xk plus d inverse b. So all of this is your M inverse N. And then this right here is your M inverse. So because N is equal to D. All right. Now, by contrast, with Gauss-Seidel, we have xk plus 1 is equal to minus d plus L inverse xk, or no, UXK plus D plus L inverse B. So right here, all of this is your iteration matrix, which I've labeled T earlier. And then this is your M inverse.
And that first line of Jacobi is it equals a negative D?
Um,
Or is that it equals a negative?
Well, the minus is
Yes.
included.
Okay, I was just making sure that's in
Okay, yeah. All right. And then finally for SOR, we have D plus omega L, wait, I'm going to move it to your side. So xk plus 1 is equal to D plus omega L inverse times 1 minus omega D minus omega U xk plus, and I have omega D plus omega L inverse B. So again, whatever's multiplying xk is the M inverse N. Whatever's multiplying B, all of that multiplying B is the M inverse. So I'll just label that. And all of this is the M inverse. Now, keep in mind, like, for instance, if I want to use that to get M, remember the inverse of a product of the inverses in reverse order, but one of those is just a scalar omega, so you can just take 1 over that. It's not a problem. Okay. Now we need the spectral radius of this to be strictly less than 1. So now we need to use that condition to get some idea of how to choose this parameter omega. Because right now we don't know anything about that. Okay. Now, getting the eigenvalues of a matrix like that is not an easy thing to do, and I'm not going to do that. What we can do, however, is take the determinant of that matrix without too much trouble. So the determinant of T is equal to the product of all the eigenvalues, assuming everything here is n by n. So it's all product of all the eigenvalues of T. And we want all of those to be less than 1 in the absolute value. So this is, so we could say that this is less than or equal to the spectral radius of T raised to the n power. For example, if all of these, if all of these eigenvalues have to be equal in magnitude, then you have equality there. Now, what is the determinant of T? So the determinant of a product is equal to the product of a determinant. So it's equal to the determinant of D plus omega L times the determinant of 1 minus omega D plus, oh wait, that's a inverse. And the determinant of the inverse, I forgot the inverse from over there. The determinant of the inverse is the inverse of a determinant. In other words, they're reciprocal. Okay. Now, keep in mind that D is diagonal, L is lower triangular, U is strictly upper triangular. This is a lower triangular matrix. This is an upper triangular matrix. So in both cases, the determinant is just a product of all the diagonal entries. So here, the diagonal entries are just the diagonal entries of A. So we have 1 over the product of all the diagonal entries. And then over here, we have the diagonal entries again, except they're multiplied by 1 minus omega. So 1 minus omega times AII. So that's the determinant of the whole thing. Well, the AII's are going to cancel. So now we're just multiplying 1 minus omega n times. So that's the determinant. So what we need to do, therefore, is if this whole we need the spectral radius to be less than 1. So the only way that that can happen is we need the absolute value of 1 minus omega to be less than 1. Now keep in mind, this is a necessary condition. It is not sufficient. I could satisfy this for a particular matrix, and the spectral radius may still be greater than 1 in magnitude. So this is just at a minimum we need this. So if we expand its absolute value, we must have omega strictly between 0 and 2. So, dang it. Okay, well, yeah. I'm sure it's not necessary, but still. Also, I may not have moved the computer enough. Okay. Oh, yep, didn't move the computer enough. Sorry about that, viewing audience. So, okay. So, well, there's also worked out in the book. So, yeah. So we must have this, omega between 0 and 2. You can almost think of omega between 0 and 1 as like under relaxation, and omega between 1 and 2 as over relaxation. Because when it's less than 1, you're not going as far along that direction from xk to xk plus 1. Omega greater 1, you are going further along that direction. I don't know if it's official terminology, but it just makes sense to me. Okay, so now we have something to go on. And in many practical applications, it turned out omega between 1 and 2 ends up being more effective, but that really varies based on the problem. How am I doing on time? Okay, still have plenty of time. Good. Okay. Now, I just want to make sure. Because I'm standing up here without notes, so I'm not forgetting anything. But I feel like I am. Now that we know something about how to use SOR, in other words, how we could possibly choose omega, one thing you could do is, for a particular problem, try a few different values of omega and get an idea of how well the method converges, if it converges, and that can give you an idea of, like, you can do some interpolation between them to choose the optimal value of omega. And in certain limited cases, there is a formula known, like for certain classes of matrices, but generally not. Okay, so now I need to state something about, are there certain situations where we know for sure that any of these methods, Jacobi, Gauss-Seidel, or SOR, are guaranteed to converge? Because fortunately we do know that in some cases. So one case in particular I can prove without much trouble. All right. So matrix A is said to be strictly row diagonally dominant if it satisfies this condition, that if you take the sum of all the off-diagonal entries in any row, so I'm excluding j equal to I, that sum of absolute values of these entries is strictly less than the size of a diagonal entry. And this has to be true for all rows. So all the off-diagonal entries in each row are dwarfed in size by that row's diagonal entry. So if a row comes from the fact that we have a condition on each of the rows, strictly because of a strictly less than, not less than or equal to, and then the diagonal dominance because diagonal entry being greater. Sometimes we just call it diagonally dominant, but this is a full term here. So if A is, I really don't feel like writing it again. I'm going to call it SRDD. If A is SRDD, then it can be said that Jacobi and Gauss-Seidel both converge. So I can actually prove it for you pretty easily for the Jacobi method. It's actually, the proof for Gauss-Seidel is harder. I don't have it off the top of my head, so you're all luck there. I can give you a reference, though. It's in my office. Okay, so how I can show this is, and it's because of a very simple form of M. So M inverse N is equal to, minus D inverse times L plus U. And now L plus U consists of all of the off-diagonal entries of A, and D consists of all the diagonal entries. So I can actually write out the entries of my iteration matrix, my T. So it would be, for instance, zeros all the way down the diagonal. And then on the off diagonal, we have a minus out front, and I have A12 over A11, A13 over A11, etc., all the way to the end. And then similar for the second row. So A21 over A22, all the way down to A2n over A22. And this just keeps going. So each entry is an off-diagonal entry of A divided by the diagonal elements in its row. Okay. Now, what I can do with this matrix is compute its infinity norm. The infinity norm is when you take the absolute value of all the entries and you add up the entries in each row. You compute all the row sums. So I could say that the infinity norm of A, no, not A, T, is equal to the maximum over all rows of the sum over all j not equal to I, because we're skipping the diagonal entry because it's 0 anyway. And then we have aij over aii. But the thing is, the sum of all these off-diagonal entries in each row, that sum is less than the size of the diagonal entry. I can factor that out, in fact, of the sum. So I have 1 over absolute value aii, and then the sum over all the off-diagonal entries. Okay. This sum, by the definition of strictly row diagonally dominant, is less than aii. And this is true for all rows. So the infinity norm is strictly less than 1. And that is the sufficient condition for convergence, so we see that Jacobi converges. So here we didn't even need to bother with a spectral radius. We can just deal with the norm. And unfortunately for Gauss-Seidel, it's a more difficult proof because you're dealing with the inverse of a lower triangular matrix instead of a diagonal matrix. So any questions about what happened here? Okay.
I'm gonna wrap my head around it.
Okay. Happy wrapping.
You know I'll ask questions.
Okay. All right. Now, one other class of matrices that I can say something about is symmetric positive definite. So if A is symmetric positive definite, but I can make these claims. Number one, that SOR, and therefore Gauss-Seidel also, is guaranteed to converge. Okay. I should mention that because SOR was obtained in the first place by putting in omega, the relaxation parameter, in a place where it used to be a 1, that SOR with omega equals 1, so now I can clearly see the contrast between my W's and my omega side by side. SOR if omega equals 1 is Gauss-Seidel. In fact, over here where I have all 3 iterations written out, if I substitute omega equal 1 in here, like this term would go away, this would become minus u, that becomes d plus l, that it reduces to Gauss-Seidel. All right, so one of the exercises, which I did not assign in the book, steps you through a proof that for any omega between 0 and 2, SOR converges. So that covers Gauss-Seidel, with omega equals 1 being included in that. Okay, so I can say that about these two methods. What about Jacobi? I have to qualify it a bit. So Jacobi converges but we need an extra condition that D, so it's not just M minus N has to be positive definite, but M plus N. So D minus L plus U. If that is SPD, so symmetric positive definite. So A is equal to D plus L plus U. So we're assuming that's symmetric positive definite. If D minus L plus U is also symmetric positive definite, then Jacobi will converge when applied to A. In fact, that's something I just looked up today. I don't recall if it was an if and only if thing. So we're just going through my memory here. May not be 100% reliable, but
Don't judge me. What is SPD?
symmetric positive definite. Yeah.
I was like, I know it's somewhere on the board.
Okay. Yeah, I can try to writing that too.
SPD.
Okay. So at least for both classes of matrices, we know something about the convergence behavior. Okay. Now, make sure I'm not missing anything.
Is that it for this box?
Yes, that's it for that box. Yeah, I have nothing more to say about the symmetric positive definite case. Okay. Oh, yes, good idea. Thank you. Okay. All right. I do have for SOR, as far as the, this is worth mentioning, the optimal choice of omega. So, whoops. All right, so if A is SPD and tridiagonal, so upper and lower bandwidth equal to 1, then the optimal omega, so in other words, it's the choice of omega that minimizes the spectral radius of the iteration matrix T, is given by, I'll call it omega star, is equal to 2 over, I wish I could remember this one off the top of my head, but no. Okay, so 1 plus square root of 1 minus spectral radius of Tj squared, where T sub j is the iteration matrix for the Jacobi method. So it's expressed in terms of that, but at least that's something you can at least get a good estimate of, especially for the case of a tridiagonal matrix. So now, so for the spectral radius for Jacobi, that has to be between 0 and 1, so we're not going to get any imaginary numbers out of this. This will be perfectly well defined. But so as this gets closer and closer to 1, then the optimal choice of omega gets closer and closer to 2. Whereas if the spectral radius of a Jacobi matrix is already close to 0, which is what we prefer for faster convergence, then the optimal choice of omega gets closer and closer to 1, which is, so SOR is more like Gauss-Seidel. I actually have done an example where I use all three methods on the same problem, like solving a differential equation. And it turned out SOR, the right choice of omega was like way, way, way faster. So in other words, it might not seem like much to have this, taking Gauss-Seidel and now just adding this tuning parameter to it. It might not seem like a big change to the method, but for certain problems it actually can be. Also, I'm going to give an example of a kind of matrix that would fulfill this condition. So if A is equal to, so symmetric positive definite tridiagonal, a matrix that has 2's on the diagonal, and then minus 1's on the superdiagonal and the subdiagonal that is symmetric, and zeros everywhere else. So this is obviously tridiagonal. It happens to be symmetric positive definite also. There is a known formula for the eigenvalues of this matrix. They're strictly between 0 and 4. So it is symmetric positive definite. So this formula would apply to this matrix. And in fact, because the Jacobi iteration matrix for Jacobi would be, so I can actually write down what that is. So it's equal to zeros on the diagonal, like over there, and then all the off-diagonal entries divided by the diagonal entries. So based on the definition over there of T, that's for Jacobi method, what are my entries above and below here? What?
Those are zeros, right?
Yeah, on the diagonal, yeah. But I think someone said it.
-1/2.
But there's a minus out front.
Okay, so +1.
Yes. Okay. And actually, so this would have a spectral radius. I think it actually gets close to 1, unfortunately, but and which drives optimal value of omega close to 2. If time permitted, then I could really get into like how we get the eigenvalues of this, but I'm going to save that for another time probably. But what I'd rather do is give a specific example of where this matrix comes up and where therefore we want to use SOR. And it comes from differential equations, which, yeah, I suppose that's a topic for later in the semester. But this, that's that later semester we're dealing with ODEs. This is a PDE, so yes, it's more advanced, but whatever. Okay, but this is a good idea of how these things are useful.
But PDEs are fun.
Yes, they are. That's why I do research in them. So as an example, suppose I'm solving this PDE heat equation. So second partial with respect to t is equal to alpha squared. The first partial with respect to t is equal to alpha squared. Second partial with respect to x. And let's suppose, I'll just make it up. The interval like 0 to 1. Okay.
I legit can't see.
Oh, okay. And I'll let h equal 1 over n plus 1, where n is the number of interior grid points. So we're solving this problem on interval 0 to 1. So I have equally spaced grid points from x1 up to xn that are interior to the interval 0 to 1. And then I impose boundary conditions at x equals 0 and x equals 1. I'll assume that the solution is equal to 0. And then we have some initial condition. Okay.
Wait, pause. Can you read that top one? That top, the part, the whole thing.
Partial derivative of u with respect to t
Okay.
And then there's an alpha.
equals
Alpha?
alpha squared times second partial derivative of u with respect to x.
Okay.
And I'll point out you are at an unfair disadvantage because you've not taken multivariable calculus yet. So it's okay. But so nothing I cover after this one will be influenced by this at all. So this is an isolated thing. Okay. All right. Now, if I were to solve this by implicit time stepping, something we will see later in the context of ordinary differential equations. Also, I didn't take differential equations either. So.
It's
Okay.
okay. You got her.
All right. Where I would solve in matrix vector form, it would look like this. U n plus 1 is equal to un plus time step delta t alpha squared over h squared times, actually it'll be minus the matrix A from over there, u n plus 1. And this comes from something that did come up in 460. This is from second partial derivative with respect to x, so like u double prime, you can think of it that way, is equal to okay, so any of you who were in 460 last semester, that might ring a bell. for approximating a second derivative. That's actually where the matrix A comes from. So now, if I rearrange this to get a system of equations for un plus 1, I'll move this to the other side. Then I have this. Now, A, I mentioned earlier, I didn't show it, but I simply told you, A is symmetric positive definite, and it's tridiagonal. Therefore, this matrix is also symmetric positive definite and tridiagonal. So what's happening is we're time stepping, computing un plus 1 from un. So we started with our initial data from our initial condition, and we compute u1, u2, u3, and so forth, one after the other. And each time we're solving an ax equals b problem. And for this problem, we can use SOR. What we can do is, since the eigenvalues of this matrix can be computed, I haven't told you the formula, but there is a formula. We can compute this. We can compute the optimal value of omega for SOR. So we can use SOR. So we know the optimal omega for SOR for this kind of problem. Just because we're solving a system involving a symmetric positive definite tridiagonal matrix. Because A, being symmetric positive definite, so it has positive eigenvalues, we're multiplying it by delta t alpha squared over h squared. That's positive. So those eigenvalues remain positive. And then we add 1 to those eigenvalues by we're adding identity. So the eigenvalues are still positive. So that's how I know from A being symmetric positive definite that this whole matrix is also. And in fact, it was for this kind of problem that SOR was developed in the first place. These kind of iterative methods that I've shown you, very often used on problems involving differential equations because they tend to involve solving systems with sparse matrices. Also, here, for a problem like this, you have a built-in initial guess. You're trying to compute un plus 1, which is a solution at the next time step from un. This is a perfectly good initial guess. Because if delta t is small, then these two are going to be close to each other anyway. Yeah. So all those reasons that I gave last time for why we prefer an iterative method to Gaussian elimination, a lot of those apply to this situation. So it's tailor-made for iterative methods, and that's what people generally use. And I can also tell you that, okay, about to run out of time anyway. SOR was introduced by a PhD student for his doctoral dissertation, David Young, way back in 1950. Yeah. You can actually dig up his dissertation. They've actually reformatted it for modern times. Something to make any graduate student out there feel like a schlub, feel like an underachiever because he comes along and does this method that's still widely in use today, when we're all just trying to get by and get our degree doing something. So now and then a PhD student can really strike gold. I think it was University of Texas. I'm not positive about that. Where he got his degree. Yeah. So. What?
Huh?
Oh, okay.
She said everything's bigger in Texas, even than brains.
I guess so. All right. So, we're almost out of time. So what we saw today was a new iterative method, SOR. That's a modification of Gauss-Seidel, which itself was a modification of Jacobi. So we continue to mess with these iterative methods. We can come up with new and in some cases very much better ones. There are some cases where Gauss-Seidel converges far faster than Jacobi. SOR can converge far faster than Gauss-Seidel for problems. In fact, problems such as this one. Now we have this parameter to choose, omega, but in some cases at least, we know what that is. And we also know when these methods, actually, okay, never mind. Class is almost over anyway. So, yeah, but we have some knowledge of certain categories, important categories of matrices for which these methods are guaranteed to converge, so we don't have to wonder about that. One involving diagonally dominant, in some cases we can tune parameters to make the matrix involve diagonally dominant, so Jacobi will converge. So I really wish I could spend more time on iterative methods because it's a fascinating field. There's a whole category of non-stationary methods that unfortunately I'll probably have to omit from the class altogether because we do have other things to get to. But it shows that whatever you would learn in your first linear algebra course, doing all those row operations on 4x4 matrices by hand, again and again and again, that there's much more to solving systems than just that. And so now you have at least, you've scratched the surface of what that's like. Okay, so that's enough. But I'll stick around for any questions. If you have questions about homework 3, which I've hardly got any of, I should hear those. So, unless you found that too easy as well.
No, it's not. It's good homework set.
Okay. Oh, even for you?
I am not that arrogant. Says the person who definitely is.
Proficient. That's what I was going for.
I'll sit here.